All right, looks like we're good now. All right, so just to, I know I already said it, but we talked about the other 3 approximation methods, and we talked about how we wanted to get as many subintervals as we could to get a better approximation. So we're going to do the 4th approximation method, which is the trapezoidal rule, or the trapezoidal approximation. And so what we do for that is we take our interval from A to B. Okay, we take our interval from A to B, we divide it up into however many subintervals we want again. And so what I've done here is sort of an arbitrary division of this into, x sub 0 is the starting point, x sub 1, x sub 2, x sub 3, all the way down to x sub n at the end. So this one would be x sub n minus 1. And instead of, like we did before, doing a left rectangular approximation like this, let's say, or doing the right rectangular approximation, so like doing something like this, right? Or rather than doing the midpoint ones, I'll just pick one here, like making them like this. We're not going to do that anymore. We're going to instead make trapezoids out of each of these subintervals. So trapezoid is just, a shape that's got two sides that are parallel, right? It's like this is a trapezoid, right? Or even, oh, that's not what I want. Something like that, right, is a trapezoid. These don't have to be equal to each other, right? You just have to have the 2 parallel bases for it to be a trapezoid. And so what we're going to do is we're going to have a bunch of trapezoids that are standing on their sides. So my first trapezoid is going to come from the value here, and the value here being my bases, and then there is that first trapezoid. So it's kind of a trapezoid standing on its end, right? It's on its side. And we're going to do the same thing for the next one. We're going to connect these 2 lines and make a trapezoid. And the same thing here. We're going to connect these 2 lines and make a trapezoid. And things get a little bit dicey, a little bit complicated if we cross through the x-axis, right? And so what ends up happening there is it ends up being 2 little triangles, but we can worry about that another time. Do another one here. We could see that trapezoid, right? Another trapezoid. We get all these different trapezoids. In fact, I might as well draw them all the way through. Okay. And we would see that sometimes these trapezoids cut off less than what the actual area underneath the curve is, right? And sometimes they go above it. And we might note that anytime the function is above the x-axis, that when it's concave down, hopefully remember the idea about concavity, right? When it's concave down, it's an under approximation. And when it's concave up, it's an over approximation. Okay. So in order to use this trapezoidal method, we have to know what the area of a trapezoid is. So somebody remind me, what's the formula for the area of a trapezoid? What's the area of a trapezoid?
The height times the base 1 plus base 2 over 2.
Height times base 1 plus base 2 all over 2, right? The average of the bases, base 1 plus base 2 over 2 times the height. And so that's what we've done here. Each of our bases are these vertical components, right? Because we said each of these is on its side. So for the first trapezoid that we have here, right? The first base is y sub 0, right? It's just the y value at x sub 0, so y sub 0 plus y sub 1 divided by 2. Times the average of our bases, and then times the height, whatever that height is going across here. And we'll worry about what that h value is here in a minute. Okay. If we had equal subintervals, each of those h's would be the same. If we didn't, then each of those h's would be different. And then we would note that the next one should just be y1 plus y2 divided by 2 times whatever this height is, and then y2 plus y3 divided by 2 times whatever this height is, and so on all the way through to the end. Does that make sense?
Yes.
Okay. So there are really only there are really only two options here. One is that the subintervals are equal. That's real easy. We'll deal with that in a minute. And the other is that the these subintervals are unequal. So if the subintervals are unequal, each of these h values is different. And you just have to calculate the area of each one of these trapezoids and then add them together. Make sense?
Yes.
Okay. Now, the easier thing would be if each of these subintervals was of equal length. And so if they were each of equal length, what could you tell me about h for each trapezoid?
You can factor it out.
Yeah, it should be equal, and we should be able to factor it out. And we'd also hopefully note that every single one of these terms also has an over 2. And each one of these terms also has a 1/2. So we could, in fact, factor out an h over 2 from the entire thing. Would you all agree with that?
Yes.
Okay. So what's left then? If I take out the h over 2 from the first trapezoids area, that just leaves me with y0 plus y1. And then this one leaves me with y1 plus y2. And this one leaves me with y2 plus y3, and so on until, let's see, how many y sub n minus 1s will I have? I'll have an extra one from the one before, right? Y sub n minus 1 plus y sub n minus 1. But at the end, how many y sub n's do I have? How many of these y sub n terms am I going to have?
Just one.
2 of them or 1 of them?
One.
Just 1, right? And so we note that the first base length, y0, was only used once, and the last base length, y sub n, was only used once, but all the rest of them were used twice, right? Right, and that should make sense if you think about it graphically, right? This trapezoid and this trapezoid share this base, so that one needs to be used twice. And these two share this one, they need to be used twice, and so on. So we could rewrite this as y0 plus 2y1 plus 2y2 plus 2y3, and so on to 2y sub n minus 1 plus only 1 y sub n. And we could adjust that formula to look like this. And this is the normal formula that we will use as the trapezoidal approximation for the area underneath the curve when all of the subintervals are of equal length. Okay, so that's the formula that you're going to want to know and be able to use. And so a couple of things about this. First is that h, the value of h, is equal to b minus a over n. So if we go back to our picture, right, h should be b minus a, so that's the length of the entire subinterval, divided by n, where n is the number of subintervals. So each one of these should have a length of b minus a over n. And second, that this should be equivalent to finding the average of a left and a right midpoint rectangular approximation. So if you already had the left and the right rectangular approximations and somebody asked you what's the trapezoidal approximation, well, all you'd have to do is say the average of those and figure out what that number is. Good or no?
Good.
Any questions on any of that? How we set that up to get that? Are we all good? By your silence, I assume that means everyone is good.
Yes.
Wonderful. All right. So then let's do this one here together real quickly. Let's use the trapezoidal rule and let's have n equal 4. And let's estimate the area from 1 to 2 of x squared. So any thoughts on how we should start that out?
I don't think we ever learned how to read that.
Oh, we didn't?
Yeah, we kind of skipped a lot of the notes.
We skipped a lot of them. No. Oh, yeah. Huh. All right. Well, you're right. Let's just do this. Well, we're going to do that later, but I don't want to do it yet. Use the trapezoidal rule with n equals 4 to estimate the area under y equals x squared from 1 to 2, which is exactly what that meant, but that's fine. We're going to worry about that in a minute. So that makes more sense now?
Yeah.
I thought we talked about that notation last time, weeks and weeks and weeks ago. All right, so all we want to do is use the trapezoidal rule to approximate how much area is underneath x squared from 1 to 2. So what do you think we should do to start with? We've got the formula, right? H over 2 right, times y naught plus 2y1 should be that area, plus 2y2. So what do we need to figure out? We need to figure out what y naught and y1, y2, and y sub n minus 1 and y sub n are, right? And we also need to figure out what h is, don't we?
Yeah.
Yes.
Yeah. So first off, we could figure out what h is from up here. Oh, yeah. And so that's, yeah, I thought we talked all about that last time. So just ignore this right now. We talked about h is equal to b minus a over n, right? So what's our b value?
Oh wait, why are we all of a sudden doing just 2 times 1 height, like 1 y value for each one again?
No, because we said that if we had equal subintervals, we could factor out the h over 2, and then we'd have y naught plus a y1 plus another y1 plus a y2 plus another y2, and so on all the way till the end until we on y sub n. So what is the h?
2 minus 1 over 4.
Yeah, it should be b, which is 2, minus a, 1, b minus a over n, and we have 4 subintervals. So what should that give us? H should be 1/4.
Yeah.
And so out in front of this, we should have a 1/8 then, right? 1/4 divided by 2 is 1/8.
Mhm.
Yeah.
Okay. And what is y not going to be?
One.
So our x naught is 1, right? And so we have to square it to get that. So 1 squared. And in fact, let's write out what all of our subintervals are. If we have 4 subintervals from 1 to 2, that should be 1, 5/4, 3/2, 7/4, and 2, right? Those are the beginning and end points of each of our subintervals. And so the first one is 1 squared, and we should add to that 2 times the second one squared, which should be 2 times 5/4 squared, and then 2 times the next one, 3/2 squared, and 2 times the next one, 7/4 squared, and then plus just 2 squared at the end. Everybody good with that?
Yeah.
Cool. So what does that come out to be? It's 1/8 of 1 plus, this is 25/16 times 2, which is 25/8. And then this one is what, 9/4 times 2, which should be 9/2. And then this one should be 49/16 times 2, which should be 49/8. And then plus 4. And what do we get? What do we end up with there? Should be 150 over 64, I think. You guys agree with that? 75 over 32?
Yeah.
Yeah. I don't think that reduces anymore. No, that definitely doesn't reduce anymore. Hold on 1 second. Okay. All right, sorry about that. Okay, any questions on that trapezoidal rule thing there? It doesn't really, I mean, that's about as complicated as it gets. If there's equal subintervals, you just use the formula. If there are unequal subintervals, you just use the trapezoid area formula and find the area of each of the trapezoids. So, good or no?
Good.
Okay. Anybody have any questions on that? I know one person said they were good, but that leaves another 30 something of you. Everyone's good?
Good.
All right. Okay. How many of you are familiar with sigma notation? Anybody or anybody not familiar?
I do not know what that is.
Do not know what that is? Okay. So there's at least one of you, which means there's probably like at least 30. Well, there's only 29 of you here today, so at least 29 of you probably don't know what that is. Sigma notation, this is just the Greek letter sigma, it's a capital sigma. It just means the sum of. Okay? That's all it means. So sigma notation is very important to us developing what an integral is, and an integral is just a way to find an area underneath the curve. So we can't do it on the back end here without knowing what sigma is. So we're going to talk a little bit about that, even though this is not really a calculus topic yet. So what this means is the sigma tells us sum of. So it says take the sum of all of these things, a sub k's in this case, from the first one to the nth one. So that means take a sub 1 and add to it a sub 2 and add to it a sub 3 all the way until I get to n. So if I said I wanted the sum from k equals 1 to 5 of a sub k, how many terms would I have in this summation?
Five.
Should have just 5 of them, right? I should have a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5. Right? We may or may not know, doesn't matter what a is, right? It's just, it's this, right? It's a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5. So what if I did something like this? What if I said sum all of the k's together from k equals 1 to 3? What would that look like? What do you think that would look like?
Would it just be 1 plus 2 plus 3?
It would be, yep. So we just sum together numbers from 1 up to 3. It'd be just 1 plus 2 plus 3. It'd be 6, right? So the sum from k equals 1 to 3 of k is 6. What if I said the sum from k equals 1 to 4 of 2k? What would that be?
The sum of 2 times each of those values.
Right. 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4. Easy enough? Right, which we could sum together and figure out what that is. It doesn't really matter what it is. It's 20, right? Exciting. We'll note that each of these is being multiplied by the 2. So this effectively could also be written with this constant, the 2, written outside the summation. These are the same thing, right? Because this would be 2 times 1 plus 2 plus 3 plus 4, right? Everybody sees that those two things are the same.
Yeah.
All right, good. So an important thing to note about summations using sigma notation is that anytime there's a constant inside of it being multiplied by something, you can take that constant out and put it in front of the sigma. And it can be factored out of it. Good there? Okay. Let's do a few more of these, and then we're going to look at a couple special cases of these that are kind of important. So let's look at the sum from, this time just for fun, we're going to start at k equals 2 and go to 4. 3k plus 1. So what do you think that should look like? What should the first term of that be?
3 times 2 plus 1.
Right, should be 3 times 2 plus 1. And then we will add to that 3 times 3 plus 1. And we will add to that 3 times 4 plus 1. Everybody good with that? Or no?
Good.
And we could obviously go in and figure out what that is. Next thing I want to talk about is, and this is going to be related to this, what if I asked you, what's the sum from k equals 1 to 5 of 7? What does that mean?
It's
Any thoughts?
7 constantly.
Yeah, it means add together all the 7s from the first 7 to the fifth 7. So that's 7 plus a second 7 plus a third 7 plus a fourth 7 plus a fifth 7. Right? Everybody would be good with that? Everyone's all right with that?
Yeah.
If I'm just summing together a bunch of constants from the first one to the nth one or the fifth one, let's say, it's just a bunch of them added together. Good or no?
Good.
All right. So let's say I had something like this. The sum from k equals 1 to 3 of k plus 2. One way we could write that would be 1 plus 2, right? For the first one would be 3, plus 2 plus 2 would be 4, right? Plus 3 plus 2 would be 5. But it could also, if we wanted, we could write it as the sum from k equals 1 to 3 of k plus the sum from k equals 1 to 3 of 2. And, we can separate this summation out into two different summations because they're being added together. Because all I'm doing here is I'm adding a bunch of things together. So it doesn't matter what order I add them in. I can add all the k's first and then add all the 2's, or I can add all the k plus 2's together. Right? This would be add together 1 plus 2 plus 3. And then this would be add together 2 plus 2 plus 2. Everybody see that? And you agree, hopefully, that those are the same thing?
Yeah.
Awesome. All right, so those are a couple of the basic rules we need to know about these summations. So now what I want you to do is I want you to tell me, I'm going to give you 2 minutes, if you can do this. I want you to sum together from k equals 1 to 100, just k. All right, you have 1 minute. Actually, you have 1 minute. Ready, go. All right, I don't know if that was enough time. I don't know if that was quite a full minute, but did you get an answer? Did you sum together from 1 to 100 of all the k's? Were you close to finishing?
Yes.
You
Yeah.
were. Were you using a calculator?
Yes.
Ah, cheaters. All right.
I got to 13.
That wasn't very fast. All right. So what I want to do now is I want to think about what this means. So what does this mean, right? We talked about this, right? This means 1 plus 2 plus 3 all the way up to 100, right? That's what this says. So what we're going to need today is we're going to need a very quick and easy way to sum together these things. So if I wanted to add these all together and I did it from 1 to 100, wouldn't that be the same as doing it from 100 to 1? I should get the same number, right? If I did this either way,
Yes.
which would mean that this would also be equal to this. True? I just wrote it backwards, but the value is still the same. True?
True.
Well, when I have two equations that I know are true, can't I add them together? Isn't that something we can do? So if I were to add these together, how many of these summations would I have? I have one of them and another one of them, right? 2 sums from k equals 1 to 100 of k should be equal to, well, if I add these together term by term, what's 1 plus 100?
101.
It's 101, right? And what about 2 plus 99?
101.
And 3 plus 98?
Oh, 101.
And 4 plus 97 and 5 plus 96 and all the way down to 99 plus 2 and 100 plus 1. They're all going to just be 101, aren't they? Do you guys agree with that?
Yes.
Okay. So 2 of this summation should be, how many 101s do I have? I should have 100 of them, right? And so the sum from k equals 1 to 100 ought to just be 101 times 100 divided by 2, which, I don't know, what does that come out to be? 5,050, I think? Is that what you guys got when you did it all together and added them all up and it took you forever?
I got 13,443.
You did it wrong then. Should be 5,050. You must have made an error typing them into your calculator or something.
Yeah, probably.
Yeah. I'm certain that it's 5,050. Isn't that cool though? That's a lot faster than doing 1 plus 2 plus 3 plus 4 on your calculator or trying to do it by hand, isn't it? Yes, the answer is yes. Yes, it is faster. So now what I want to do is I want to, instead of having 100 of these, I want to have some arbitrary amount. I want to come up with a generic formula for this. So I want to sum together from 1 to n the integers. So what does that look like? It looks like 1 plus 2 plus 3 all the way up to almost n, right? N minus 1, and then up to n, right? If n was 1,000, this would be 999 and 1,000. Or if n was 732, this would be 731 and 732. Good or no?
Good.
Okay, great. Well, using the same logic as before, this summation could also be written in the opposite way. And now when I sum them all together, each term is what? When I add those together, what do I get?
N plus 1.
And when I add those together, what do I get?
N plus 1.
N plus 1. And when I add the next ones together, I'm going to get N plus 1. And the next ones will be N plus 1. And all the way up till I get to N minus 1 plus 2 is another N plus 1. And N plus 1 is going to be another N plus 1. Everybody agree with that?
Yeah.
And how many of those N plus 1s do I have? I should have 1, 2, 3, 4, 5, 6, 7, 8, N of them, right? I should have N of them. And so what does the sum from 1 to any number equal? It equals that number times the next number divided by 2. Everybody see how we got that?
Yeah.
Cool. This is a very important formula because it allows us to do some really cool stuff here in a minute with what we call integrals. Okay? This is something you're going to want to know. You're going to need to be able to use that. Good or no?
Good.
Okay. Oops, I should have put a K in there. Sum from K equals 1 to N of K is equal to N times N plus 1 over 2. Then I'm going to put one more page in here. We're not going to prove this one if you want to go online and look at the proof of this. The sum from K equals 1 to N of K squared. You should know this one also. This is N times N plus 1 times 2N plus 1, all divided by 6. You should know that. So this is the sum of all the squares, like 1 plus 4 plus 9 plus 16 plus 25 and so on, will always equal this. So if I want to know the squares of all of the first 10 integers, so 1 squared plus 2 squared plus 3 squared all the way up to 10 squared, it should be 10 times 11 times 21 divided by 6. You can amaze your friends and family with this if you wish. I'm sure you all wish to. Amaze them. Amaze your friends and family. Be like, I can add together the first 73 square numbers much faster than you can, Mom. And then you show them how much better at math than you are. And yeah, you seem less excited by this than I do. Oh well. Maybe it's just because it's Monday and you've forgotten everything about math that you ever learned after 2 weeks off. Does that sound about right? Yeah. Or you're all asleep and just not talking. That's good too.
A little bit of both.
A little bit of both. Nice. All right. I mean, I can always, it's a shame because if we were in my classroom, you'd be awake because I'd be like screaming and throwing things and banging the board. But if I throw things in my house, my children will be like, you get mad at me when I throw things. And something, I don't know. All right. So that's the basics of sigma notation in these summations. So you need to know this one and you need to know the one above, right? This one right here. And we're going to use these to help us find the exact area underneath pretty much any curve we want. We're going to start with some easy ones. All right. Everybody good with the summation stuff?
Yeah.
Okay. So what we're going to do then is we're going to sort of go back to that last, remember I drew this like a graph that sort of looked like this for the trapezoidal approximation. In fact, it was probably this exact graph. So, and what we're going to do is we are going to draw midpoint rectangles underneath here. So I've drawn a couple here. I've drawn one here. And rather than labeling these x sub 0 and x sub 1 and x sub 2 and x sub 3 and x sub 4 and 5 and 6 and so I've taken one interval, and it doesn't matter which one, it's just an arbitrary one. I could have chose any interval and called it the kth interval. Okay, so we've just denoted it as a k. And it's important to think about why we chose k. It doesn't really matter what letter we chose. We chose k because it's going to be like these k's in our summations, right? We had all these k's in our summations. And what we're going to want to do is we're going to want to use a summation to sum together the areas of each of the rectangles. And so we're just picking k as a variable to represent any of them. This one is k equals 1. This one is k equals 2. This one is k equals 3, k equals 4, k equals 5, and so on. Does that make sense?
Yeah.
Okay, cool. So what we have done in the past is we said, take your rectangle and find the area of it, and find the area of the next one, and find the area of the next one, and find the area of each of the rectangles, and sum them together. And that gives us a nice little approximation of the area under the curve. So what we're going to do is we're going to come up with the formula for the area of the kth rectangle. So what is the area of this rectangle right here? It should just be a length times a height, right? Or a base times a height, or a length times a width, or however you want to call it. So what is the height of that rectangle?
C of k.
Well, so that's the x value at which we went up. And so the y value is the height, right? The y value is f of c sub k, which is always my favorite one to write out, because f of c sub k, it kind of looks like a bad word. Oh, look at that. Oh my goodness. How scandalous. All right. And then we also have a base here, right? What's the base of this rectangle? What's the length from here to here? It's x sub k minus x sub k minus 1. And so what we're going to call that is, it's just a change in the x value in the kth subinterval. So we're going to call that base delta x sub k. Easy enough?
Yeah.
Okay. So the area of any of these rectangles is f of c sub k times delta x sub k. And what we want to do is we want to sum together all of these areas from the first rectangle, where k is 1, right? So f of c sub 1 times delta x sub 1, that'd be the area of this rectangle, plus f of c sub 2 times delta x sub 2, that'd be the area of the next one, and f of c sub 3 times delta x sub 3 would be the third one, and so on. You guys all agree with that?
Yeah.
Or no? Yeah? Okay. So if we were to write that in a summation notation, it should look something like this. The sum from k equals 1 to n, because we don't know how many subintervals we have. We have an arbitrary number of subintervals. The sum from k equals 1 to n of the heights times the bases of each subinterval. Everybody see where this summation formula comes from?
Yeah.
Okay. And what this is called is also called a Riemann sum, right? We've talked about, right, Riemann approximations. I think did I call them Riemann approximations sometimes, or no? I might not have. When we were doing our approximations?
No.
No. Okay. This is a new term. This is called a Riemann sum, right? And a Riemann sum is just a summation that represents the area underneath some curve. That's all a Riemann sum is. And so this is a Riemann sum for some function f on our interval from A to B. And as we talked about before, if we had the lengths of the subintervals get smaller and smaller and smaller, that would mean we would have more and more subintervals. And what would happen to our approximation for the area underneath the curve?
It would become more accurate.
It would become more accurate, right? And so that's our goal, is to get more subintervals. So we want n to be a larger number so that we can then get a better representation of that area. And so if we think about this sort of, we've already used this formula and we just didn't know we were using it when we did our midpoint rectangular approximations. You know, we did a midpoint rectangular approximation with 4 subintervals, right? And we just found the area of each one and we added them together. Well, now our goal is going to be put into this summation notation and use some of these things here that we've just learned about summations so that we can have a larger value for n and not have to do so much arithmetic and just plug it into a formula that we know. Does that make sense? That's our goal. Good or no?
Good.
Okay, wonderful. So we have a couple of things we have to deal with first before we can do that. One is that, are each of these subintervals of equal length?
No.
Just by a visual inspection, right? We're going to say no. X sub 0 to x sub 1 looks a whole heck of a lot smaller than x sub 1 to x sub 2 or x sub k minus 1 to x sub k. Would you all agree? They don't appear to be of the same length. Okay. So since they're not of the same length, we have to take the largest one and try to get the largest one to be very, 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 very small. We want to shrink them all down at the same rate so that the biggest one gets very, very close to 0. And let's say this one is our biggest one. I think it looks a little bit wider than that one maybe. So we want this one to go towards 0. And if we shrink all of them down at the same rate, so like I divide them all in half, and then divide them all in half again, and then divide them all in half again, as this one gets to be very, very close to a length of 0 from x sub k minus 1 to x sub k, what's happening to all the other ones also?
They'll have already reached 0.
Yeah, they're also getting smaller and smaller and getting closer and closer to 0. And so this largest subinterval we call the norm of the partition. It's called the norm of the partition. And so what we want to do is we want to make the norm of the partition approach 0. And the notation for the norm of the partition is this p within 2 double bars. That's called the norm of the partition. It's the largest subinterval on this partition of our function from A to B. And it's a lot of words and a lot of notation, but that's what it's called. So we want to make the norm of the partition, this double bar P, approach 0. Well, we have a problem with that. What's the problem with that? If it's going to be 0, what are all the other ones going to be?
Equal to or less than that.
Equal to or less than that. We can't have a negative interval, obviously. So they're all going to be basically at 0 eventually, true? And if all of those things have a base of 0, your delta x sub k is 0, isn't it? And that's just going to make this whole thing 0, won't it? And if I sum together a bunch of zeros from the first one to the nth one, 0 plus 0 plus 0 plus 0 is just going to be 0, right?
Right.
Yes.
And we know that this area is clearly not 0. The area underneath this curve is not 0. So how can we make this thing get very, 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 very close to 0, but not actually be 0?
A limit.
A limit. That's right. So what we're going to do is we're going to take the limit as the norm of the partition approaches 0 of this sum from k equals 1 to n of f of c sub k times delta x sub k. And this, if I could make those intervals so small that they were effectively 0, I'd basically have an infinite number of those subintervals. And that would mean that instead of having an approximation for the area underneath the curve, I should get an exact value for the area underneath the curve. So all we have to be able to do is evaluate the limit of this summation of the area of one rectangle, of one arbitrary rectangle, K, and that should tell us the exact area under the curve. Does that make sense conceptually? I know it's a lot, but that's the concept of what we're doing. The math behind it is actually going to be about 1,000,000 times easier than conceptualizing that. So do we understand what we're doing? It's really important that we understand what's going on.
For the most part.
For the most part. Anybody have any questions on it?
We're basically just making our n as small as possible, right?
Not our n, because remember, n represents the number of subintervals. So in a second, we're going to rewrite this into an even easier limit, but we're not making n as small as possible. We're actually making n as large as possible, right? We want to have as many subintervals as we possibly can. What we're doing is we're making the length of those subintervals very, very small. Does that make sense?
Yeah.
Okay. All right, cool. So this is the nasty equation that we have to find the exact area underneath the curve. And if we go through here, let's see, we've got a limit, we've got a summation, we've got a function f of something, and we've got p, we've got k, we've got n, we've got c, and we've got x. So we have a limit, we have a summation, we have a function, and we have 5 different variables. That's a pain. Would you agree?
Yes.
Yes. Now, unfortunately, there's nothing we can do about the limit. We're still going to have a limit. There's nothing we can do about the summation. Bummer. And there's still nothing we can do about the function. But we should be able to sort of normalize things a little bit and get rid of some of these 5 variables that we have to make life a little bit easier. So one of the issues that we started with was we had to deal with this norm of the partition. We had to look at the largest subinterval, right? And we said this one was bigger than all the other ones, so we called that one the norm of the partition. But couldn't I, for any subinterval, couldn't I always make equal subintervals?
Yes.
Yeah. So rather than trying to make one of them approach 0, we could have each subinterval be equal. And if each subinterval was equal, then rather than making one of them approach 0, we could just make the number of them. We could make n approach how many subintervals do we want to have to get an exact area?
Infinity.
An infinite. So we could just make n approach infinity. And so, yeah, blah, 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 all this stuff. Don't bother with that. What we're going to do is we are going to try to change this into a limit as n approaches infinity of a new summation from k equals 1 to n of the heights. And since we decided instead of having each of those subintervals to be a different length, we now have them all the same length. The widths of each of those rectangles will all be the same. They'll all just be delta x rather than delta x sub k, right? The length of that subinterval. The length of each subinterval will be the same. It'll always be equal to b minus a over n, which is the starting value minus, or sorry, the ending value minus the starting value divided by however many subintervals we have. And so this is going to be better limit and summation. So all we've done is we've taken this one, the limit, and I'll look at it here, the limit as the norm of the partition approaches 0. Instead of doing that, we're no longer having norm of the partition, we just have a number of subintervals approaching infinity. And we still have a summation from k equals 1 to n of f of c sub k times delta x sub k, except now the sub k is no longer relevant because each of those subintervals has the same length. And so they all just become delta x's. Good or no?
Good.
Okay. So I'm going to say it one last time here, unless somebody needs me to say it again. This right here, this is the area of each rectangle. And we are summing together sum all of the areas. And then we are looking for the limit as we have an infinite number of n represents subintervals. So we'll say subintervals. But really, it's an infinite number of these rectangles of which we're summing the areas together. Okay. And this whole thing is called an integral. And this has a specific name. It's called a definite integral. A definite integral, where we are finding an exact value for the area underneath the curve. And this, for now, is the formula that we are going to use to do that. Any questions on that? I know that's a lot. That's a lot of just information without doing any problems per se. But luckily, you won't have to repeat anything that we've done today. You'll just have to be able to use the formula. But it's really important to know where it's from. Well, you'll have to repeat the trapezoidal formula that we did. But everybody good there or no?
Yes.
Okay. We got a few minutes. What time are we at here? At 10:04?
Yes.
Or is it 4 or 14? I can't.
4.
4. Yeah, of course you would say that. All right. So let's see if we can relate this to this other notation first. This is the notation that I accidentally threw in there earlier. This is called the integral notation, or it's called Leibniz's notation. So this notation, it's really annoying. Should probably capitalize that in. This is Newton's, and this is Leibniz's notation. Two different people that were like, making calculus at the same time. Newton's notation had this limit and this summation, and Leibniz introduced this new sign in here, which is called an integral sign, okay, which effectively just says, all right, do all this limit summation crap, except that's what this thing means. That makes sense?
Yeah.
Okay. So what we need to be able to do is we need to be able to convert back and forth between Newton's notation and Leibniz's notation, because we're going to want to use Leibniz's notation the majority of the time. Even though to start with, we're going to use Newton's notation because you need to know it for the AP text. So this little squiggly stretched out S thing is called an integral sign. It's got a lower limit, which is the beginning of our or the beginning of our interval. It's got an upper limit, b, which is the end of our interval. It has the function inside of it, which we call the integrand, and it has this little dx there also. And so we're going to talk about what all those things are and how they match up. So first off, the limit of the summation is just this integral from a to b. Okay? And then f of c sub k is just the f of x. And delta x and dx are effectively the same thing also. So the delta x represents the width of the rectangle. Wow, that's really poorly written, but and so does the dx, right? The delta x and the dx represent the width of the rectangle and each of the rectangles. And how wide are those rectangles? How many of those rectangles are there?
An infinite number.
And so how wide are each of them on some given subinterval?
Very close to 0.
Yeah, we'll call them the widths of those rectangles. We say they are infinitesimally small. Right? They're basically 0. And so a lot of people, when we start talking about this notation, get worried about this dx and what it is. Just remember that dx, it just represents the widths of these rectangles that we are summing together for the areas. The f of x is the height, the dx is the width. Okay? So let's see if we can take this limit and this information that's been given to us and write this as an integral in Leibniz's notation. You think we can do that?
Sure.
Yeah. So we're taking an interval from -1 to 3, and we are going to partition that into n subintervals of equal length. And m sub k, rather than c sub k before, it doesn't matter what letter we use. M sub k is the midpoint of the kth subinterval. We want this to be an integral. So first off, we need an integral sign. There's my integral sign. Where are we integrating from? Where are we finding this area from?
-1 to 3.
From a lower limit of -1 to an upper limit of 3. That came from right there. Okay. What is the function that we are looking at? It comes from this, doesn't it? Should be 3x squared minus 2x plus 5. And the delta x should become a dx. And that is this limit expressed as an integral. Okay, so that's taking it from Newton's notation. This is Newton into Leibniz. Good or no? Any questions on how we went from Newton's to Leibniz's?
So this limit is solving for an area technically, right?
That's exactly what it's doing. Yes, this
Okay.
limit is the area underneath this curve, 3x squared minus 2x plus 5, from -1 to 3. Specifically from -1 to 3 because that's what we set up here. Right? Yes, this limit finds us the area underneath this curve on any subinterval that, or any interval that we want. Good or no?
Did you just replace the m sub k with x?
Yep. And because this is the midpoint of it at any point, right? M sub k is just the midpoint of any subinterval. And so to find the height of the rectangle, we just plug that x value that we got, that midpoint, m sub k, into the function. And so 3m sub k squared minus 2m sub k plus 5 just tells us that we've gone up from whatever x value we wanted, 3 times that x value squared minus 2 times that x value plus 5. And that's just what our function is. So like if this was sine of m sub k in here, this would be sine of x in here. Good or no?
Good.
Okay. Any questions before we stop for the day because we're not going to have time to do the next problem in its entirety. Everybody's good?